Dear students, I am Khandakar Fazle Rabbi, lecturer, Milestone College, Uttora, Dhaka. Today, I discuss with you about Le-Chatelier principle and application of Le-Chatelier principle. Dear students, today we discuss about Le-Chatelier principle. What is Le-Chatelier principle? When any system at equilibrium is subjected to change in concentration, temperature, volume, or pressure, then the system readjusts itself to counteract the effect of the applied change, and a new equilibrium is established. We can also say that if we can also change that if we change concentration, temperature, or pressure, to a reversible reaction at equilibrium, if we change concentration, temperature, or pressure at a reversible to a reversible reaction at equilibrium, then the then equilibrium will try to undo the change made. This is Le-Chatelier principle. You can write this one or this one. Now, there are three ways by which the equilibrium can be changed. There are three ways by which equilibrium there are three ways by which equilibrium can be changed. First one, changing the concentration of the reactant or product. This one is first one, changing the concentration of the reactant or product. Second one is changing the pressure, and third one changing the temperature. By these three ways, the equilibrium can be changed. Dear students, now we discuss about the change of concentration, that means effect of concentration on equilibrium. Let us consider a gaseous reversible reaction. Nitrogen plus 3 hydrogen produce ammonia. Gas. Now, if we add nitrogen, at equilibrium, then the concentration of nitrogen increase and the equilibrium will disturb by the adding nitrogen. Then the equilibrium will try to undo the change, and equilibrium shift to forward reaction to decrease the excess concentration of nitrogen. Forward. Again, if we decrease the concentration of hydrogen at equilibrium, then also the equilibrium disturbed, and equilibrium will try to undo the change, and equilibrium shift to backward reaction to increase the concentration. Shift to backward. Now, if we remove ammonia from the equilibrium state, ammonia remove, then the equilibrium also disturbed by the remove ammonia, and equilibrium try to undo the change, and equilibrium shift the reaction forward. Shift to forward. Here we learned that if we add small amount of, or if we add reactant at equilibrium, then the equilibrium disturbed, and equilibrium try to undo the change, and equilibrium shift the reaction toward forward. And if we decrease the concentration of product, then equilibrium also disturbed, and equilibrium try to remove try to undo the change, and equilibrium also shift to forward. At a glance, we can say that if we add reactant, equilibrium shift, shift to forward. If we remove product, at equilibrium state, then a new equilibrium will established by shift the reaction forward. Equilibrium shift to forward. And if we remove reactant, then equilibrium shift to backward, and if we add product, then equilibrium shift to backward. Now we can discuss for another reaction. If we consider the reaction sulfur dioxide plus oxygen, reversible reaction sulfur trioxide. If we want to increase the production of sulfur trioxide, increase the production of sulfur trioxide, at first we have to increase the concentration of sulfur trioxide or increase the concentration of oxygen. If we increase the concentration of sulfur dioxide or oxygen, then the equilibrium disturbed, and equilibrium try to undo the change and forward reaction occur. And another way to increase the production of sulfur trioxide, that is, if we remove sulfur trioxide, then equilibrium disturbed, and equilibrium try to undo the change and forward reaction occurs, and our production will increase. This is the effect of concentration on equilibrium. Now we discuss about the effect of pressure on equilibrium. Here rule is increase pressure. If we increase pressure at equilibrium, then equilibrium shifts to that direction which has lesser number of moles. If we decrease pressure, equilibrium shift to that direction which has greater number of moles. Now if we consider the reaction N2O4 to NO2, here lesser number of moles we get from reactant. So if we increase pressure, then the reaction go backward because the lesser number of mole is here. Equilibrium shift to backward. If we decrease pressure, then the equilibrium disturbed and equilibrium try to undo the change of pressure and equilibrium shift to forward. These two reactions. If we consider another reaction such as nitrogen plus 3 hydrogen, reversible sign to ammonia, here we see that the lesser number of moles present in product. So if we increase for this type of reaction where mole number of product is lesser than the mole number of reactant, for this type of reaction if we increase pressure, then equilibrium shift to forward. Equilibrium shift to forward because product has lesser number of moles. Forward. And if we decrease pressure, equilibrium shift to backward. Again, I repeat, for this type of reaction where mole number of reactant is lesser than the mole number of product, for this case, increase of pressure, equilibrium shift to backward, and for decreased pressure, equilibrium shift to forward. And for this type of reaction where mole number of product is lesser than mole number of reactant, for this case increase of pressure, equilibrium shift to forward, and decrease pressure, equilibrium shift to backward. And For this type of reaction, hydrogen plus iodine to HI. For this type of reaction, where mole number of reactant is equal to the mole number of product, for this type of reaction, pressure has no effect. Pressure has no effect. And this is the effect of pressure on equilibrium. Students, now effect of temperature on equilibrium. We see there are two-way effects of temperature on equilibrium. The first one is on the position of equilibrium, and the second one on the equilibrium constant. Now, effect of temperature on the position of equilibrium. We know that according to heat release and heat absorption, reactions are two types. First one is exothermic reaction and second one is endothermic reaction. At first, we discuss about exothermic reaction. Let us consider one reaction, nitrogen plus hydrogen ammonia plus 92.4 and del H equal to minus 92.4 kilojoule per mole. This one is exothermic reaction. That means heat is released in this reaction. Now, if we increase temperature, if we increase temperature for this type of reaction, that means for exothermic reaction, the equilibrium disturbed, and the equilibrium will try to undo the change of temperature, and the equilibrium shift towards backward. Equilibrium shift backward. And if we decrease the temperature, the system will try to neutralize the effect of temperature. If we decrease the temperature of this reaction, the system will try to neutralize the effect of temperature reduction, and the equilibrium shift towards forward and towards right, or the equilibrium shift forward, and we get maximum product. That means decrease temperature, equilibrium shift to forward. That means for exothermic reaction, if we want maximum production, then we have to decrease temperature. And if we decrease temperature, then reaction will forward, and we get maximum product. And now for endothermic reaction, if we consider the reaction nitrogen plus oxygen to NO minus 180 kilojoule per mole. That means del H, here del H equal to plus 180 kilojoule per mole. Now we see that this one is an endothermic reaction. Here heat is absorbed by the reactant, and according to Le-Chatelier principle, if we increase temperature of this reaction, then the reaction the equilibrium try to undo the change, and the equilibrium shift to forward. That means increase temperature, equilibrium shift to forward. And if we decrease the temperature, then the reaction try to undo the change, that means the system undo the change or neutralize the effect of changing the temperature, and the equilibrium shift to left, or equilibrium shift to backward, decrease. Decrease temperature, equilibrium shift to backward. And this condition is for endothermic reaction. And we see that for exothermic reaction, this condition is for endothermic reaction. That is endothermic reaction. And for exothermic reaction, increase temperature, equilibrium shift to backward, decrease temperature, equilibrium shift to forward. Here, for exothermic reaction, effect of temperature on the position of equilibrium. For exothermic reaction, if we increase temperature, then the equilibrium will shift to backward, and if we decrease temperature of the reaction, then equilibrium will shift to forward. And for endothermic reaction, increase temperature, that means if we increase temperature, then the equilibrium shift to forward. And for endothermic reaction, if we decrease temperature, the equilibrium will shift to backward. Now, effect of temperature on the equilibrium constant Kp. We know that when temperature is fixed, then the equilibrium constant also remain unchanged. But when we change the temperature, then the equilibrium constant also changes. The effect of temperature on equilibrium can be explained by Van 't Hoff equation. Here I write Van 't Hoff equation log Kp equal to minus del H divided by 2.303 R into 1 by T plus constant. This equation is y equal to mx plus c type equation, and here del H equal to change of enthalpy, T equal to absolute temperature, and R universal gas constant. For endothermic reaction, we see that increasing of temperature increases the rate of reaction. That means it increases the value of Kp. And for endothermic reaction, we get this type of graph figure, change of Kp with temperature in endothermic reaction. If you see here, if you increase temperature, then the value of Kp increases for endothermic reaction, because if we increase temperature for endothermic reaction, the rate of reaction also increases, and that's why the Kp value also increases. For exothermic reaction, we get this type of graph. For exothermic reaction, we see that if we increase the temperature, then the reaction rate decreases, and for that reason the value of Kp also decreases. That's why this graph is like this one. That means if we decrease temperature, then if we increase temperature, then Kp value also decreases, and we get this type of graph for exothermic reaction, and this type of graph we get for endothermic reaction. Now, application of Le-Chatelier's principle on industrial production. There are important applications of Le-Chatelier's principle in industrial production, but here we discuss about the synthesis of ammonia using Haber-Bosch process. In industry, large amount of ammonia is produced from nitrogen and hydrogen using Haber-Bosch process. You see the reaction: nitrogen plus 3 hydrogen, product is ammonia, and here we get del H equal to 92.4 kilojoule per mole. Now, effect of temperature. We see that this reaction is exothermic reaction. So, according to Le-Chatelier principle, if we decrease the temperature, then the equilibrium try to undo the change and the reaction go forward. But rate of reaction is slow at lower temperature. Hence, to increase the rate of reaction, a favorable temperature is selected at which the rate of reaction and total production become profitable. This temperature is known as optimum temperature. In Haber-Bosch process, uh, the optimum temperature is 450 to 550 degree centigrade temperature. Now, effect of pressure. In this reaction, the number of moles is reduced from 4 to 2 moles. Hence, according to Le-Chatelier principle, an increase in pressure should increase the production of ammonia. Experimentally, it has found to be true, and pressure of 200 atmosphere is used in industry to get a reasonable and economical profitable production of ammonia. Now, effect of concentration. We know that according to Le-Chatelier principle, if we increase the concentration of reactant, then the reaction go forward, and if we remove product at equilibrium, then the reaction also go forward. For ammonia synthesis, here if we use addition of reactant, that means if we add nitrogen or hydrogen at equilibrium, then the reaction go forward and we get maximum ammonia from this reaction. Or if we remove ammonia from the equilibrium, then the reaction move forward and we get more and more ammonia. And the last one is use of catalyst. Catalysts are used to increase the rate of reaction and to reach the equilibrium rapidly. Catalysts do not have any effect on equilibrium. By increasing the reaction rate, catalyst acids to reach the equilibrium rapidly. For ammonia production, iron powder is used as catalyst, and molybdenum oxide or a mixture of potassium hydroxide and aluminum oxide are used as catalyst promoter. Thank you.